While electric vehicles, EVs, produce zero tailpipe emissions, making them better for air quality compared to gasoline or diesel vehicles, they are not entirely pollution-free. A comprehensive understanding requires considering their entire life cycle, from raw material extraction to disposal or recycling. Sources of pollution from electric vehicles. Manufacturing. The production of EV batteries is energy-intensive and involves the extraction of materials like lithium, cobalt, and nickel. This process can lead to significant environmental impacts, including habitat destruction, water pollution, and greenhouse gas emissions. Some studies suggest that manufacturing an EV can create more carbon pollution than manufacturing a gasoline car due to the battery production. Electricity generation. The environmental benefit of an EV heavily depends on the source of electricity used for charging. If the electricity comes from fossil fuel power plants, like coal, the EV indirectly contributes to air pollution and greenhouse gas emissions. However, research indicates that even with the current electricity grid in many places, EVs still typically produce lower life cycle emissions than comparable gasoline or hybrid vehicles. As the electricity grid transitions to cleaner and renewable energy sources, solar, wind, hydro, the overall emissions from EVs decrease significantly. For example, in regions with low polluting energy sources, EVs have a clear life cycle emissions advantage. Conversely, in regions heavily reliant on conventional electricity generation, this benefit might be less pronounced. Battery lifespan and disposal recycling. While EV batteries are expected to last for a considerable time, around 10 to 15 years or 180,000 to 200,000 kilometers, their end-of-life management is crucial. Improper disposal can lead to environmental contamination due to the hazardous materials they contain. However, EV batteries can often be repurposed for second-life applications, such as powering homes or buildings, extending their useful life before recycling. Recycling technologies are also developing to recover valuable materials from used batteries for new production. Non-exhaust emissions. Like conventional vehicles, EVs produce particulate matter pollution from tire and brake wear. Due to the heavier weight of EVs due to the battery, some studies suggest that they might generate slightly more of this type of pollution compared to gasoline cars, although next-generation EVs might only see a small reduction, 4 to 7% for PM10, and a potential increase of 3 to 8% for PM2.5 according to the OECD. Electric vehicles as a pollution alternative. Despite the pollution associated with their life cycle, EVs are generally considered a better alternative to traditional internal combustion engine vehicles in the long run, especially as electricity grids become cleaner. Zero tailpipe emissions. This significantly improves air quality in urban areas, reducing health issues related to vehicle emissions. Lower greenhouse gas emissions. Over their lifespan, EVs typically result in lower overall greenhouse gas emissions compared to gasoline cars, and this advantage will grow as renewable energy use increases. Energy efficiency. EVs are generally more energy efficient than gasoline cars, converting a higher percentage of energy into motion. Alternatives to electric vehicles for sustainable transportation. While EVs are a key technology for reducing transportation emissions, several other alternatives and approaches contribute to more sustainable transportation. Hydrogen fuel cell vehicles, FCEVs. These vehicles use hydrogen to generate electricity, emitting only water vapor. Green hydrogen, produced using renewable energy, makes FCEVs a very clean option. However, challenges remain in hydrogen production, storage, and infrastructure. Biofuel-based vehicles. Vehicles running on biofuels like ethanol and biodiesel, derived from renewable organic matter, can have a lower carbon footprint, especially if the biofuels are sustainably sourced. They can often be used in existing internal combustion engines with little to no modification. Hybrid electric vehicles, HEVs, and plug-in hybrid electric vehicles, PHEVs. These combine an internal combustion engine with an electric motor and battery. PHEVs offer the ability to drive on electric power for shorter distances, reducing reliance on gasoline. Hybrids improve fuel efficiency through regenerative braking and electric assist. Sustainable public transportation. Investing in and improving public transportation systems like electric buses, light rail, and trains can significantly reduce individual vehicle use and overall emissions. Active transportation. Promoting walking and cycling through better infrastructure, sidewalks, bike lanes, offers zero-emission transportation with added health benefits. Car sharing and carpooling. These practices increase vehicle occupancy, reducing the number of cars on the road and associated emissions. Sustainable fuels for existing vehicles. Development of synthetic fuels produced from carbon dioxide and hydrogen, using renewable energy, could potentially make internal combustion engines carbon neutral. Natural gas vehicles. Vehicles running on compressed natural gas, CNG, generally have lower emissions compared to gasoline or diesel vehicles and are a more readily available alternative fuel in some regions. In conclusion, while electric vehicles have environmental impacts associated with their production and electricity source, they generally represent a significant improvement over traditional vehicles in terms of air pollution and greenhouse gas emissions, especially as the energy sector decarbonizes. A truly sustainable transportation system will likely involve a combination of EVs, alternative fuels, efficient public transport, and a shift towards active mobility. CBG, compressed biogas, and RNG, renewable natural gas, are both sustainable and environmentally friendly alternatives to conventional fossil fuels like CNG, compressed natural gas. While they share similarities, there are key distinctions. Compressed biogas, CBG. Source: CBG is produced by purifying biogas, which is generated through the anaerobic decomposition of various organic materials. These materials include agricultural residues, e.g., crop stalks, rice husks, cattle dung, sugarcane press mud, municipal solid waste, organic fraction, sewage treatment plant waste, other waste streams like rotten vegetables, food waste, and poultry litter. Production process. The biogas produced typically contains 55 to 60% methane, 40 to 45% carbon dioxide, and trace amounts of other gases like hydrogen sulfide. To produce CBG, this raw biogas undergoes a purification process to remove carbon dioxide, hydrogen sulfide, water vapor, and other impurities. This results in a gas with a methane content of over 90%. Properties and usage. CBG has a calorific value and properties similar to CNG, making it suitable for use as a green renewable automotive fuel in vehicles designed for CNG. It can also be used in industrial and commercial applications. Transportation. CBG can be transported to retail outlets via cylinder cascades or pipelines. Benefits: reduces reliance on natural gas and crude oil imports, utilizes waste materials, reducing emissions and pollution, supports national climate change goals, provides income for farmers and rural employment, contributes to the Swachh Bharat mission through waste management. Renewable natural gas, RNG. Source: RNG is essentially biogas that has been further processed and purified to meet pipeline quality standards, making it interchangeable with conventional natural gas. The biogas used to produce RNG can come from the same sources as CBG, including landfills, landfill gas LFG, wastewater treatment plants, livestock farms, food production facilities, organic waste management operations. Production process. Similar to CBG, biogas is produced through anaerobic digestion or thermal gasification of organic matter. It then undergoes an upgrading process to remove impurities like water vapor, carbon dioxide, hydrogen sulfide, nitrogen, oxygen, and other trace contaminants. This purification increases the methane content to 90% or greater, typically between 96% and 98% for pipeline injection. Properties and usage. RNG is chemically identical to fossil-derived natural gas. Therefore, it can be used in all applications where natural gas is used, including heating and cooking, electricity generation, vehicle fuel, as CNG or LNG liquefied natural gas, feedstock for bioproducts, transportation. RNG can be injected into existing natural gas pipelines for distribution. It can also be compressed, CBG, or liquefied, bio-LNG, for transportation and use in vehicles. Benefits: reduces greenhouse gas emissions by capturing methane from waste sources, utilizes existing natural gas infrastructure, increases energy security and diversifies fuel sources, can provide revenue or energy cost savings, improves local air quality. Key differences and similarities. Purity. RNG undergoes more extensive purification than CBG to meet the stringent quality standards for pipeline injection and interchangeability with fossil natural gas. CBG, while also purified, may have slightly less stringent purity requirements as it is primarily used as a vehicle fuel or in localized applications. Interchangeability. RNG is fully interchangeable with conventional natural gas, meaning it can be seamlessly blended into the existing natural gas pipeline network and used in any natural gas-powered equipment. CBG is primarily used as a direct replacement for CNG in vehicles and some industrial applications, but might not always meet pipeline injection standards without further upgrading. Transportation. While both can be used as vehicle fuel, with RNG being usable as both CNG and LNG, RNG's pipeline compatibility offers a broader transportation and distribution network. CBG typically relies on compressed gas cylinders or dedicated pipelines to reach end users. Nomenclature. Sometimes, the terms can be used somewhat interchangeably, with CBG often being referred to as bio-CNG, which is a form of RNG used as compressed gas for vehicles. In essence, both CBG and RNG are produced from biogas and represent significant steps towards sustainable energy. RNG is a more highly purified form of biogas that can seamlessly integrate with existing natural gas infrastructure, while CBG is specifically processed for compressed gas applications, primarily as a vehicle fuel.